Hello, my name is Varun Kohli. I'm a security engineer in Microsoft Sentinel team. In this video, I'm going to demonstrate how we can use Microsoft Sentinel to detect abnormal behavior in network traffic. For this, I'm going to use an analytic rule that would help us to detect anomalies in network session logs. Although this analytic rule is focused on analyzing the network logs, but we can use the similar approach for detecting anomalies in different logs like DNS, authentication, web session, etc. I'm going to talk about two functions that we used in this analytic rule, the time series functions. Those are make series, series decompose anomalies, and I'm also going to share a function that we can use to detect future values or do a forecasting of values as well. And at last, I'm also going to talk about an approach that you can utilize to improve your KQL query performance. So let's first look at the analytic rule to detect anomalies. Okay, I'm on Azure portal currently. I'm on the Microsoft Sentinel page. The analytic rule that we will use is part of a solution called Network Session Essentials. Network Session Essentials is a solution that you can find inside Content Hub. I have already installed this solution in my workspace. So let's look at what content we have in this solution. So a solution would contain different content types. A solution may contain data connectors, analytic rule, playbook, hunting query, or workbook. Even this solution contain a number of content. The one that we're going to focus on today is this one, detect port misuse by anomaly-based detection. In order to get a better view, let me take you to GitHub. This is the Microsoft Sentinel GitHub repository. The content that you would find inside the content hub, you can you can also locate the same content on the GitHub repository as well. If you noticed, we were looking at network session essential solution in the content hub. So network session same content are also available on this page on GitHub, and we are looking at the same analytic rule. So in case you want to check out a content, you can either see the details in Content Hub, install the solution, see the details in Content Hub, or you can directly come to GitHub and check out the details or look at what that content is actually does, what it does. Okay, so let's look at this analytic rule and try to understand what this analytic rule does. So the first thing that this analytic rule is doing, it's analyzing past 14 days of data. So it's going to analyze data for last 14 days. It's reading a watch list with name network session monitor configuration. What is watch list? You can think of a watch list as a configuration file. So that this watch list can be used to pull some additional information or do some enrichments that would be useful for our incident creation. So let's look at the watch list, what the watch list actually contain. So this watch list actually contains a list of network ports. So since network ports can be in an environment can be in hundreds or maybe in thousand, so we would not want our analytic rule to analyze each and every network port. We would want our analytic rule to analyze and focus only on some of the critical specific network ports. So what we have in this watch list are specific network ports that our analytic rule would read and only focus its detection. So if you look at one example, the first row, so this is for the port number, network port number 389. So we have a column called threshold type anomaly. So what this means, whatever network ports that you would see with threshold type anomaly would be eligible for our anomaly based detection. So whatever network ports that you see are there with the anomaly, only analytic rule will only analyze those network ports. Severity as high basically means whenever there is an anomaly detected on this particular port, the incident that gets created will be created with a high severity. And with the tactics, information like initial access and execution, and the names and description will be dynamically pulled out from this watch list. Okay. So let's go back to our rule. So it reads past 14 days of data. We have seen that it's reading a watch list. Now the next thing it's doing is trying to summarize and take out the fields that it wants to focus on. So this rule is only looking at these fields out of the network traffic. So it's looking at field network protocol, which contains values like TCP, UDP, ICMP, different network protocols. It's looking at uh, destination port number, destination app name, network direction, could be like inbound, outbound, DVC action, can be like allowed, denied, etc. So it's only focusing on these fields and it's trying to get the total request count. So this is what the data it's focusing on. So before actually going into details about how this rule uses the time series function and detects anomalies, let me let me actually take you to let me take you to the Sentinel back to the Sentinel portal, Azure portal, and show you how an incident looks like uh, when triggered by this analytic rule. So I have already configured on my workspace this analytic rule, and it has actually created an incident. So this is how an incident looks like. So as an analyst, if I see an incident that says unusual network activity identified on port 3389. So if I see this, I would understand that there is um, there is maybe some anomalous traffic on this port port 3389, which is for remote desktop. So what it means is there is there's significant increase or decrease in the amount of traffic on this port number in the last 24 hours. So I can probably look at what this port number is used for by looking at the description. So all these names and description that you see has been pulled from the watch list, and it has been enriched. This incident has been enriched with with those details. We can see the tactic and techniques has been populated as well. And let's see what other details we have. So it also it has also added some of the custom details like network protocol is TCP. I can see the DVC action is deny. So basically the request has been destined to the port number 3389 where the DVC action was denied. And I can see that the total request count is showing as around 8,675 on this port number, where the baseline it predicted was 3,000. And yeah, it's a significant higher number, three times the almost three times the baseline. And it is, I can see that there's an anomaly score of 5.9 as well. So uh, I can see the incident now. Uh, Now let's look at how it has actually uh, came to the conclusion that there is a anomalous behavior on this port number, and how these all baseline and the anomaly score is calculated. for this, I'm going to switch to my Kusto Explorer. So the data that the analytic rule is analyzing the network logs. So I have taken sample of network logs from Palo Alto PanOS. Palo Alto PanOS is a firewall from Palo Alto, and these are the raw logs, raw network logs that the analytic rule is analyzing. So if we try to understand what this log is, I can see that there is a count column, which basically means there is a 304 count of request to this port number 5060 on this network protocol where the DVC action was reset destination. So our analytic rule has actually summarized this data to its required form. And let's see what next it's doing. So the next step that the analytic rule does after summarizing the data is creating the time series. So the line number 88 make series function is used for creating this time series. And we have created a time series on the total request count that we have done. We are doing a sum of request count um, on time for the last 14 days uh, and doing granularity or the bin by 1 day. So the output of this function is we're going to get a numerical array of the total request count for each day for last 14 days. So let's take an example. So the total request for the last 14 days is this for this port number 54890. So the numbers that you are seeing here, 1645, 1670, are actually the request count for 1 day. Uh, we have these 14 different values for each one for each day and with this combination. So for every network port combination with DVC action, it has created this time series. Similar to the numerical array, we also have an array for our time, um, our date time field, which basically contains the list of date time for last 14 days for each combination. Okay, so at this point, we have got our time series. The next step is to actually run our um, anomaly data model functions to detecting anomalies. So series decompose anomaly is a function, is an out-of-the-box function that we use in this analytic rule to detect anomalies. Series decompose anomaly function is based on a data model called seasonal trend decomposition model. This function, series decompose, is actually based on that data model, um, and the component that we get out of this function are actually used for creating the or for generating the anomalies. So let's look at the component first, and let's see how we can how we use this function. So series decompose function, you can see we have a function name. We are passing on the our time series that we calculated in the previous step. We are passing on a couple of parameters. So -1 is used for auto detecting seasonality, and we have a line fit, which is an approach for calculating the trend for a linear regression type of trend. Um, so once we call this function series decompose, we get some of the component out of this, right? So let's look at them one by one. So this is our the actual traffic on port 3389. So what I've done here is for simplicity, I have just filtered the traffic going to port 3389 with a deny request out of the total network traffic. So we're only seeing one type of traffic here. Uh, and you can see this traffic is for last 14 days, but we have a spike at one point. Um, so the first component that this model calculates is the seasonality graph. Seasonality actually tells us the instances which are known, which happens on a fixed frequency. So that's we get as a seasonality. The another component that we get is trend, which tells us in which direction our data is going, whether it's a positive trend or a negative trend. Based on the seasonality and the trend components, the third component that it calculates is the baseline. So for each instance, it gives a predicted value. So at the point where we see a spike in the traffic, uh, you can see we have a baseline that it predicted was 3,427, where actually we have the total was 8,600. So we see there's a significantly higher than what it predicted. So the last component that it calculates is the residual component, which is calculated based on the trend and the baseline. So let's now look at the actual function that we use in the that is used for calculating the anomalies. So the function is series decompose anomaly, like I mentioned, is used for calculating the anomalies. But the other function that we saw are actually this function is based on that function. So the residual function or residual component is what is used for calculating the anomalies. So let's see how we can use this function series decompose anomalies. So we pass on the time series as one of the input. Um, so you can see we are passing on the total, which is our time series numerical array, as one of the input. We are giving an anomaly threshold input as well. So anomaly threshold is used for controlling whether you want a stronger anomaly or a mild anomaly. 1.5 is actually the default anomaly parameter. 2.5, I'm using 2.5, which basically means we need a stronger anomaly, slightly stronger anomaly. So I'm using auto seasonality -1, and I'm using line fit for our trend approach. So let's look at what the component that we get out of this function, series decompose anomalies. So this is our traffic, same traffic I'm using. So we are seeing the traffic to port 3389 with that are denied. So this is our time series for that port request. The one component that we got is the baseline. So this is the predicted values or the baseline that it calculated. Based on the baseline score and the trend, it calculated the anomaly score. So you can see that at the point where we have a spike, we can see that we have a score of anomaly score of 5.9, uh, and then the last component that we get is actually telling us where the anomaly exists. So that's how we can use this function to detect anomalies in our logs. And like I mentioned earlier, you can use the same approach for detecting anomalies on different data. Although this example was focused on the network, but you can use similar approach for detecting anomalies on different kind of data as well. Okay, so we created time series. We used the anomaly function to detect anomalies, and I actually ran the whole analytic rule, and this is how our final output looks like. So like we saw earlier, it actually joins or enriches our output with the information provided in the watch list. So based on the time series, we got an anomaly on this port 3389, and using this port number, it joined the information that was present in the watch list, and we that's how we got the name and the severity, the description, and these values were calculated based on our function as well. So the total count was 8,000, whereas it predicted, as per the prediction, the baseline was supposed to be 3,000. So the request count is significantly higher than it expected. So it considered it an as an anomaly incident, and it given a score of 5.9, anomaly score of 5.9. In the analytic rule that we have, line 60, line number 95, we are filtering the records which have a score of around greater than 5. So any score, any anomaly score that's greater than 5, we will take it as a detection. So that's how it we extracted that there is a we came to a conclusion that there's an anomalous behavior on this port number. Um, Now let's look at our third function, which can be used for detecting future values. So series decompose forecast is a function, is another out of the box function that you can use to for calculating the future values. So if you have a use case that requires you to do some predictions for future values, like maybe you have a server for which you want to predict the performance, so you can utilize this function for for detecting future values. So to take an example, what I have taken is I have filtered out the network traffic going to port 443 on this network protocol. So what we're seeing here is a network trend going to port 443 for last 30 days. The drop that you're seeing here are actually the future dates. That's what we don't have currently the request count. That's why we are seeing the drop. So the at line number 85, we are using series decompose forecast, and we are passing on the same time series numerical array as an input, and as a second input, what we are providing is we are asking this function to give us future predicted values for the next 7 days. So if I select the forecast, this is what it has forecasted. So we can see the last 7 days or future 7 days forecast for the request count on this particular port. So this is an example of how you can use series decompose forecast function for predicting future values. At last, I would like to share an approach of data summarization that can be used to improve your query performance. So um, uh, you can see we have on the left side, I have a raw data which I have filtered to get a specific type of data. So here what I have done, I've done a filter on the network logs to give me the request on port 22, which have DVC action as deny and network protocol as TCP. So after running this query, I am left with 1591 records, number of rows. So, and on the right side, uh, the same uh, the same data, instead of instead of uh, getting the raw data, I have actually used a summarization query where I'm using a count of these combinations. So the data that you see on the left uh, is actually the raw data, and on the right side you can see we have a summarized data, both representing the same kind of data or the request, which is actually going to port 22 with a deny request. So now. Uh, if I run an analytic rule on a raw data, it would need to process 1591 rows. Whereas if I run a analytic rule on the right side, which is on the summarized data, then my analytic rule need to process just one row, and it would improve my analytic rule performance. So this is just a simple example to show you uh, how using summarized data to run an analytic rule can help in specific scenarios where you may have a lot of data to analyze, and maybe you're getting timeouts, or your query is taking too much time. So you can summarize your data, store the summarized data into in a specific table, and then run your analytic rule, um, and run your analytic rule to actually on the summarized data instead of the raw data. So just to share an example, the analytic rule that we just covered has this capability that not only it can read the raw data, but it can, if it will check whether there is an existence of the summarized table, then it will give precedence to that table, and it will read from the summarized table. So what is happening here is, as part of this rule, we have a playbook that we use for reading the raw data and ingesting and creating summaries of the raw data and ingesting the result or the summaries into custom tables. So one of the custom table that you're seeing here is this one, network custom analytics protocol. This actually contains the summarized network data, and this rule is actually reading from that table. So this reading from the summarized table improves the analytic rule performance, um, and you can use a similar approach for doing creating your own summaries, and we can use playbooks for automatically ingesting or creating those summaries. So coming back to our presentation, so just to summarize what we covered, we saw an analytic rule, and we saw how an anomaly was detected on a network log. We saw the time series functions to detect anomalies and for predicting forecast values and forecasting future values. And we also discussed the an approach uh, for creating summaries. We also discussed an approach for creating for an approach for improving your query performance using summarization. Hope this information was useful to you. Let's see you in another video. Thank you.